So we know the wavefront set of a distribution U is a subset of the domain of the distribution times a punctured plane, which is Rn without the origin. So the question I'm asking in this video is, what happens when you take the projection of the wavefront set of a distribution onto this part here, this variable here, into omega? What happens? So if we have any intuition on the theory of microlocal analysis and the wavefront set as it was defined in the previous videos, we might guess that this is equal to the singular support of U. And we would be correct, because the intuition that I gave is that U is that the wavefront set is a refinement of the singular support. And so this is actually precisely what I mean when I say that the wavefront set is the refinement of the singular support, that the projection is the singular support. So today we're actually going to try to prove this. And one of the first, because of how intuitive this statement seems, one might be tempted to think that the proof is actually pretty simple if we know Paley-Wiener theorem, for example. And one direction actually is, but one of our first indications that the theory, that the wavefront set in microlocal analysis is a richer theory than you might expect, or that it has a certain richness to it, is that proving this very intuitive fact, it seems like a fundamental result, is not immediate given the Paley-Wiener theorem. And so let's begin the proof. So this is our theorem that we're looking to prove. And before I give the proof, we're actually going to need two lemmas. So lemma one is another pretty intuitive fact. It is that it's actually a characterization. It's a characterization. So if we have U, a distribution, if x0 is a point in the domain of the distribution, and it's not in the singular support of the distribution, meaning if we have x0 here, there is a little neighborhood of x0 where the distribution restricted to that neighborhood is C infinity. So here U is C infinity. So if this is not the singular support of U, that's actually the same thing as saying, that there exists a phi, a cutoff function of phi, that is equal to 1 on a neighborhood of x0, and the Fourier transform of the localized version of U, so U localized, actually decays rapidly. So we have this bound here. This Fourier transform is less than or equal to some constant times 1 plus xi to the minus n, and this is for all n positive integers, and for all xi in Rn. So for all directions. So saying that U is C infinity in a little neighborhood around x0 is the same as saying that the Fourier transform of the localized version of U decays rapidly in all directions, at this point at least. So this is our first lemma. The proof of this one is actually pretty simple. It's just an application of the Paley-Wiener theorem. And we have our second lemma. This one has a bit more of an involved proof. It involves some creativity and bounds, and, analysis arguments. And this one talks about distributions of compact support. So suppose I have a distribution U of compact support. Then what this one states is that, well, let me first say that, so if you, how should I say this? What is the best way? So if there exists a direction, let's say, or an open cone, say an open cone gamma xi 0, so the open cone around the direction xi 0, such that the Fourier transform of u, and this is why we took u compact support, so the Fourier transform would make sense. So we took the Fourier transform of u. If this decays rapidly, so this is my new quick notation for rapid decay. I'll just do this arrow going down and 0. So if the Fourier transform of u decays rapidly on this open cone here, then for any other closed cone, for any, let's say, gamma xi 0 prime closed cone, such that it is, I can say it like this, a closed cone in gamma xi 0, we have the same bound. Same bound on the decay of the Fourier transform of u, except now it's a localized version of u. So you have the same bound on, oh sorry, we had to choose a phi first. So such that scale rapidly on this, then for every phi, and this phi is going to be a cutoff function, so in the same way we always choose phi, right, equals 1 and around a neighborhood of, actually, yeah, just a cutoff function. There is no x0, so this is just a cutoff function. This is in C infinity, C of omega. So then there would exist a closed cone slightly smaller than our original open cone, such that the same bound applies on now phi u, Fourier transform of phi u. So this also goes to 0. So it goes to 0 in this guy, in this closed cone. So what we're saying here is that if we have a distribution u, so let's say we have u here, and u decays rapidly in this cone, then if we take phi a cutoff function, and then we localize u according to that phi, we will have rapid decay not along this original cone, but along a slightly smaller cone. So if we multiply phi, we sacrifice this little margin of rapid decay. But essentially, we preserve the direction at least. Okay, so this is lemma 2. And now we can get to proving the theorem. So proof of the theorem, that the projection of the wavefront set is equal to the singular support. And let's just rewrite the theorem. Projection of the wavefront set of u. U is the distribution on omega. This is the singular support of u. Okay, so first let's do this direction here. So we're going to do this guy is contained in this guy. We're gonna prove by contrapositive, or I don't know how this argument is actually called for sets. It might not be called contrapositive. What I'm going to do is I'm going to take a point that's not in this guy, the complement of this one, and show it's in the complement of this one. So suppose x0 is not in the singular support of u, which would mean, again, that around x0, there's a little neighborhood such that u is C infinity here. Now, by lemma 1, so this is the same thing as saying there exists a phi cutoff function around x0 such that the Fourier transform of the localized version of u decays rapidly in every direction, in all directions. Okay, and this essentially proves it, because we wanted to show that x0 is not in the projection of the wavefront set of u. And in fact, what does it mean to be in the projection of the wavefront set of u? To be in the projection of the wavefront set of u, that means there must exist, so for x0, there must exist a xi0, right, in the cotangent space, such that there's an open cone around, so we have x0 here, xi0 such that there's an open oh sorry, not an open cone, just such that, well, such that this is in the complement. This is in the complement of the C infinity set, essentially. So we can't have rapid decay along this direction. But there is no direction. There is no direction such that this does not have rapid decay. Every direction has rapid decay for, in fact, for a fixed phi. So this can't be in the projection of the wavefront set. We have rapid decay in all directions. So this is the easy direction of the proof. And now we have the other direction. So we're tempted to say in this direction the same thing. After all, why can't we just retrace our steps and say that, so if x0, if we're proving it in the same way, like this contrapositive argument, we suppose that x0 is not in the projection of the wavefront set of u, meaning there is a direction xi0 such that this guy is not in the C infinity set of u. So this is not in the C infinity set of u, okay. And then we would like to get that this is not in the singular support. Right. So yeah, this is not a singular support, so that u is C infinity around x0. Why can't we just apply lemma 1? Why can't we just apply lemma 1 and say, well, since x0 is not in the projection of the wavefront set, that means there is a direction such that there is no rapid decay, so the direction would be xi0, for example. And that means that we don't have rapid decay in all directions. And so that means we can't be, x0 not being in the projection of the wavefront set actually means that there doesn't exist this direction, right? So I'm making a hypothetical incorrect direction of proof and getting confused. So this would be a hypothetical incorrect direction. We would suppose that x0 is in the projection of the wavefront set, is not in the projection of the wavefront set, and that would mean there is no direction xi0 such that we have rapid decay in that direction. And so we would use lemma 1 to get this. And so that doesn't work, because for x0 to not be in the projection of the wavefront set, that means that yes, we would have rapid decay in all directions. So in this side we'd have rapid decay, in this side, that xi1, we would have rapid decay, and so on, we have rapid decay in all these. But for each one of these cones, remember, the wavefront set doesn't establish rapid decay, it establishes rapid decay of a localized distribution. So first, before getting rapid decay in this cone, we would need to take the Fourier transform of some phi u, and this phi depends on the direction, so it depends on xi. So phi xi1 of u Fourier transform of that would decay rapidly here. Here we would have phi xi0 of u Fourier transform of this would decay rapidly here, and so on for all the cones. So the problem is, so we can't reverse this simple argument here, because in this case, the direction of rapid decay depends on the cutoff function phi with respect to whom we localize before taking the Fourier transform. So we're going to need to account for that. What we need to do is, so we know that x0 is, we're going to still start assuming that x0 is not in the projection of the wavefront set, and that would give us rapid decay of a localized u in every direction, but this rapid decay would depend on phi. So what we need to do is remove the dependence on phi, and that would solve the problem. So let's in fact start with this hypothesis. Let's start by saying that x0 is not in the projection of the wavefront set. Okay, so if this is not in the projection of the wavefront set, that means that for every direction xi0, well, for every direction xi, there exists phi, a cutoff function, infinity c and omega, such that phi equals 1 on a neighborhood of x0, and an open cone call it gamma xi, such that localize u here with respect to gamma with respect to xi. Fourier transform of this decays rapidly on this open cone xi, and this is for all directions. So this is what it means. So this is just the definition of this. And so what we have now, what we need to use now is, oh yes, and notice of course that so this phi depends on psi. What we need to do is remove this dependence on xi, right? And the first step is noting that to each direction we associate a point on the sphere Sn minus 1. So this is kind of the creative step here. We're going to use the fact, the crucial fact here is that the sphere is compact. So note that for each psi is actually associated to a point on the sphere, right? Each of these points is actually a direction. So we're going to first cover the sphere. Let's cover the sphere using these xi's. So what am I going to do? Let's define a set. It's calligraphic C. And let's just define it here as the intersection of the sphere with, let's go with my gamma xi's here. Yeah. With these gamma xi's. What? This is not writing. That's strange. The pen is now stopped working. Let me pause this for a second while I fix the pen. Okay, so the pen seems to be fixed. Where were we? Okay, so S minus 1. So we're constructing a set. We're constructing a cover for the sphere. So we could apply a compactness argument. So this cover C is S minus 1 intersected with all the gamma xi's. And we'll do xi. I mean, we can go for complete overkill here. I mean, we could do, let's do xi in S minus 1. Something like this. And so this would be a covering of the sphere that would look something like, have just a bunch of arcs. A bunch of arcs here that correspond to projecting the cones onto the sphere. So this would cover the sphere. This would be an open cover of the sphere, and so by compactness, of the sphere, we can take an open subcover that's finite. And so there would exist, j equals, let's go j from 1 to m. Yes, j from 1 to m, such that, let's do gamma psi j. So this union here, indexed by j, this is a finite union of, we would also want to intersect these actually with Sn, right? So Sn minus 1 intersected with this gamma xi j. So this is also a cover of the sphere. Great. And so now we have, so we have finitely many directions. This is already good. We have finitely many directions. Therefore, we have associated finitely many phi's. Right, so we went from infinitely many phi's to finitely many phi's. Let's try to get down to one phi that matters. What we can do here is, let's see if we can already apply lemma 2. Yes, but before applying lemma 2, let's just state, so we have, of course, phi xi j associated to each gamma xi j. So we have one of these associated to each of these, and these phi xi j's, of course, are of all of those type, all cutoff functions around x0. And so since there are finitely many of them, so finite many phi xi j's, this implies that we can take the intersection over all j's of the supports of these guys, these phi xi j's, and we'll define that as v, right? So we could actually take something slightly smaller. Let's do or. Slightly smaller, just to be safe. So we take a little neighborhood around x0 that is contained in the supports of all of these. In fact, actually, better yet, not supports. Not supports. We don't want this. We want. Oh yeah, we want supports. Let's call this support with a squiggly line on top. Support with a squiggly line is not the closure of the place where this guy is positive, but so let's do support with a squiggly line means closure of set where phi psi j is identically equal to 1. So we want basically the smallest neighborhood around x0 such that all of our phis, all of our phi xi j's are equal to 1. That's what we want. Right, so why do we want this? Well, now because, so this is the crucial part. Other than the compactness part, this is the other creative part, which is the use of lemma 2. So now lemma 2 implies, so remember lemma 2 was that if we have a U distribution of compact support such that the Fourier transform along a direction, Fourier transform in this cone decays rapidly, then we can localize that U according to some test function, and it will still decay rapidly in the same direction, just along a slightly thinner cone. So that's lemma 2. And we can now use lemma 2 to note that there exists a test function, let's call it just phi, just regular phi, such that, let's go with phi test function, such that phi is 1. Yes, let's go phi, actually. Let's see phi supported. Yeah, let's do phi supported on V. So actually this is a test function on V. Yes. So we have this neighborhood V here, where all of our other phis, so on this V, all these phi xi j's are 1. And now we want this phi does this in this neighborhood and is 0 everywhere else. Okay, so this is what we're doing. And we take a phi like this, and now according to lemma 2, we had rapid decay, right? We had rapid decay of phi xi j times u, right? Phi xi j times u for all j. So we had this rapid decay on gamma psi j for all j. This is what we had. Rapid decay of all these guys. And so lemma 2 would give us, since phi is a test function that satisfies the hypotheses of lemma 2, we can now say that phi times phi xi j u, we can say that this has a Fourier transform which decays rapidly on gamma xi j prime, where gamma xi j prime is that slightly thinner cone, closed cone inside gamma xi j. And in fact, we're not going to take this to be a closed cone. Let's take this to be an open cone, slightly smaller than our closed cone given by the lemma. So this is open cone such that the closure of this gamma prime xi j is the one given by the lemma. Okay, so anyway, this is a slightly thinner cone, and it's slightly thinner, satisfying a condition. So the condition it satisfies is that all of these guys, union over j of these gamma xi j's, still cover the sphere. So in other words, we still get all directions. So these still give us all directions. And this is the important part. Still give all directions. And so this goes to 0. So we have rapid decay of this along all directions, which is what we wanted. But we wanted this for not phi xi j u. We wanted just u to be here. However, notice that because of this condition here, because of the way we define v, we have that phi of phi xi j u is actually equal to phi u, right? And so this is exactly what we want. We now have phi u here, and the Fourier transform of this decays rapidly on every direction, specifically in these directions given by the gamma prime psi j's, right? Finitely many of those. And so we've removed now the dependence on phi. We have a single phi that works. And so now we can apply lemma 1. And we are finished. So that's the proof of this seemingly, this definitely fundamental fact about wavefront sets, whose proof is definitely more involved than one would expect. And so, yeah, that's the main thing I had to show for today. I also wanted to comment on another very cool theorem, but whose proof is just immense, so I won't do that, but the proposition is just very nice, and I don't think I wanted to wait another week to talk about this one. So there's another theorem, which is not as intuitive as this last one, not as expected, actually, as this last one, but just very useful, which is that the wavefront set of U, a distribution U, is contained in the wavefront set of PU, where P is a linear partial differential operator, and it can't have variable coefficients. So just the general kind, union with VP, where VP is the characteristic set of P. And the characteristic set of P is just a set of points where the principal symbol is 0. So this is the roots of the principal symbol. So this VP appears in many places, for example, in the definition of an elliptic operator, and also, for example, in Hormander's condition for hypoellipticity, where he characterizes hypoellipticity of constant coefficient linear differential operators. So this is a very important set. In the propagation of singularities, it also appears. And so what this essentially says is, well, when we have a PDE, a linear PDE, it's usually written in this form. So PU equals F. P is a differential operator. U is an unknown distribution, and this is a known distribution. So most regularity problems involve, you know the regularity of this. Let's say it's C infinity on a certain region of the domain. And we want to discover what regularity properties U has. And we would like U to be C infinity as well. And the hypoellipticity of P actually guarantees this. So I think I talked about this in one of the videos. I might not have. So if this is hypoelliptic, by definition, we have this P actually transfers the regularity of F onto U. So PU C infinity implies that U is C infinity, which is what we want. We get regularity of solutions. Another way to write that P is hypoelliptic is to say that the singular support of U is contained in the singular support of PU. So we already have actually the singular support. It's an earlier property that the singular support of PU is contained in the singular support of U. This is called locality. This is a property of locality. And so this locality, says that P does not increase the singular support of U. So it doesn't create any new singularities. And this is hypoellipticity. Hypoellipticity says the exact opposite. Not only does P not create these singularities, it also doesn't remove singularities. Like, it doesn't create singularities backwards, so to speak. Right. So it doesn't increase the singular support and it doesn't decrease. It exactly preserves the locations of your singularities. Right. Exactly preserves them. If we have hypoellipticity as well as locality. And so this notion is very important in like the classical analysis. And in wavefront sets, we have an analogous notion, which is microhypoellipticity. It's essentially the same thing, except when you have a differential equation of this type, microhypoellipticity implies that if P of u is not C, so P of u C infinity implies u is C infinity, whereby C infinity I don't mean C infinity in the traditional sense, I mean it in the microlocal sense, like you choose a direction, apply the wave, C infinity as in the complements of the wavefront set is what I mean. So this is microhypoellipticity, and it can be written as this condition here without the VP. And so this theorem is interesting because it says that if an operator fails to be microhypoelliptic on a certain region of the domain, then this must be the fault of the characteristic set. So in other words, outside of the characteristic set VP, every operator P is certainly microhypoelliptic. So it preserves singularities, and not only does it preserve the singularities, it preserves their direction as well. Right. So yeah, so that's just the statement of this really cool theorem that I wanted to share. And next time, I'll probably wrap up this classical part about the wavefront set, so we can start talking about pseudodifferential operators and generalize this stuff and give applications.